The third part of this video is calculating the outlet pressure when given the inlet pressure. Now, we are going to use the general flow equation to solve this particular problem. But before we do that, we need to calculate the compressibility factor. The compressibility factor is not given, and we are going to use the CNGA method to calculate the compressibility factor. The CNG method is Z equal to 1 over 1 plus average pressure times 3,344,400 times 10 raised to power 1.785 G, all divided by the fluid temperature raised to power 3.825. So that is it. And where the average pressure is in the average pressure, which is in PSIG. The average pressure is in PSIG, while the average temperature, not average, why the temperature of the fluid, the temperature of the fluid or gas is in Rankine. Sorry, in Rankine. So now we need to calculate the average pressure, and the formula for average pressure is 2/3 bracket open P1 plus P2 minus P1 times P2 divided by P1 plus P2. Now, where the pressure, the now we know that the outlet pressure is equal to 9,000 kilopascal. Since it's 9,000 kilopascal, and the average, let's assume that the average, sorry, let's assume, no, the inlet pressure is 9,000 kilopascal. Let's assume that the outlet pressure is 0, but we don't know. Now, what we are going to get as the average pressure will now be 2/3 of 9,000. So this will give us 2/3 of 9,000. Let's use our calculator. 9,000 times 2 divided by 3 will give us 6,000 kilopascal. So this is the average pressure. So now, but we need to convert the average pressure to gauge pressure. So we need to convert the average pressure to PSIG. So now, so the average pressure, which is equal to 6,000 kilopascal, will now be 6,000 kilopascal times 0.1 7 psi divided by 1 kilopascal. So, to convert this 6,000 kilopascal to PSIG, 1 kilopascal is equal to 0.147 PSI. So now we're going to make use of our calculator to calculate 6,000 times 0.147 give us 8. It will now be equal to 882 PSIG. So now we have gotten our average pressure. Now, assuming the temperature of the gas is 15 degrees Celsius, so converting this to Fahrenheit, it will now be 59 Fahrenheit. Now, this 59 Fahrenheit to Rankine will now be 59 plus 460. This will give us 519 for Rankine. So that means the gas temperature is 519 for Rankine. Now, applying the CNGA method, you now have the compressibility factor equal to 1 divided by bracket open 1 plus another bracket average pressure times 344,400 times 10 raised to power 1.785 G divided by the temperature of the gas raised to power 3.825, all in brackets. So now we now have 1 divided by 1 plus the average pressure of the gas is 882 times 344,400 times 10 raised to power 1.785 times 0.6, all divided by 519 raised to power 3.825. So let's now use our calculator to calculate this. We now have now let's calculate this one first, or I can do the whole at once. 1 divided by bracket open 1 plus bracket open 882 times 344,400 times 10 raised to power bracket open 1.785 times 0.6 bracket close divide by 519 raised to power 3.825 bracket close bracket close equal to, so 0.872, 0.872, that is our z. Now that this is z we're going to use to do this calculation. So now the compressibility factor. Now let's apply the general flow equation where the flow rate is equal to 5.747 times 10 raised to the power minus 4 times the transmission factor times the ratio of the base temperature divided by the base pressure, or in brackets P1 square minus P2 square divided by GTFLZ, all bracket close, all raised to power 0.5 times D raised to power 2.5. Now, where from this equation, from this flow equation, where Q is equal to the flow rate in meter cube per day, that's the units, the flow rate of the gas. So now you have the F, which is the transmission factor. This one is dimensionless. Then we have the base pressure, the base temperature, which is what, in kilopascal, sorry, which is in Kelvin, Then we have the base pressure, which is in kilopascal. We have the upstream pressure, upstream pressure, or the inlet pressure, which is in kilopascal. We also have the downstream pressure, which is in outlet pressure. This is in kilopascal. We have G, which is the gas gravity. This is dimensionless. Then this is the fluid temperature. This is in Kelvin. This is the pipe segments length, which is in kilometer. We have the compressibility factor. This is dimensionless. Now we have D, which is what, our internal diameter. Now we have calculated our internal diameter to be 380. That is what we used here. Yeah, to the 380. Look at it here. So now this is the formula we're going to use. So now we're supposed to solve for the downstream pressure or the outlet pressure. Now we are given the flow rate equal to 5.747 times 10 raised to power minus 4 F times the base temperature divided by the base pressure times bracket open P1 square minus P2 square divided by GTF Z all raised to power 0.5 times D raised to power 2.5. Now we know our F to be equal to 18.11. Sorry, 18.11. We know our base temperature to be 288 Kelvin. We know our base pressure to be 101 kilopascal. We know our inlet pressure or upstream pressure to be 9,000 kilopascal, and 9,000 we need to convert this. This is in gauge. This is the gauge pressure. We need to convert it to absolute pressure by adding the base pressure. So it will now be 9,000 plus 101. This will give us what? 9,101 kilopascal. So absolute. So this is the absolute pressure. Now we have our G to be 0.6. We have our fluid temperature to be 288 Kelvin. We have our pipe segment length to be 48 kilometer. We have our Z to be 0.872. 0.872, let's see. 0.872, correct. So we have our D to be 380 millimeter. So now internal diameter is what? It's in millimeter. So now let's now solve for the downstream pressure or the outlet pressure. So this is the final part of this um, question, which is part 3. The final. So now let's solve for it now. First, let's try to make P2 the subject formula. So now for us to do that, we divide the both side of the equation with this whole this the whole of this term and this one, and also this. Now if we do that, what we're going to do now, we're going to have P1 square minus P2 all raised to power 0.5 will equal to, now if you look at this, this is dividing this. So if it goes to this side, it becomes multiplication. You're multiplying this with this. So we have Q times bracket open G times T times L times Z all raised to power 0.5 to multiply this. So now while this where this one, which is multiplying this expression, will be dividing this. So divide by 5.747 times 10 raised to power minus 4f. Now, this d raised to power 2.5, which is multiplying this, will also be dividing this here now. So divide by 2.5 times. Now, if you divide by the ratio of temperature over pressure, you will now reverse it to be pressure all over temperature. So that is it. So now we have finally taken the whole of this off there. Now, so this is what we're going to get. Let's calculate this expression, see what it gives us. So now the Q is equal to 3.5 times 10 raised to power 6 meter cube per day. So we're going to put that here. So we have 3.5 times 10 raised to power 6 bracket times 0.6 times the temperature 288 times the length 48 times 0.872 all raised to power 0.5 divided by cannot enter there. So let's bring it down again. Cannot enter. So let's say equal to the flow rate is 3.5 times 10 raised to power 6 times the G is 0.6 times the temperature is 288 times the length is 480 times the compressibility factor is 0.872 all raised to power 0.5 divide by 5.747 times 10 raised to power minus 4 times F, which is 18.11 times density times internal diameter, which is 380 raised to power 2.5 times base pressure, which is 101 divided by the base temperature, which is 288. So the whole of this is equal to 1. Now let's use our calculator to do this. Now we have 3.5 exponential 6 times bracket open 0.6 times 288 times 48 times 0.872 bracket close raised to power 0.5. Okay, times this 101 divided by 288 divided by 5.747 exponential minus 4 divided by F, which is what 18.11 divided by 380 raised to power 2.5. So we have 3,563 points. We have 3,563.108. The whole of this is 3,583.108. So let me see and be sure. Okay, 563.108. So this is 63. So we have P1 square minus P2 square all raised to power 0.5 equal to 3,600, 3,563.108. Now, if we square both sides, we now have P1 square minus P2 square equal to 3,563.108 all squared. Now we have P2 square will now be equal to P1 square minus 3,563.108 square. So we have P1, which is 9,101 square minus 3,563.108 square. So what we are going to have for P2, taking the square root of both sides, you now have this 9101 square minus 3563.108 square. So now let's make use of our calculator here. So this x value, if we square it, it's minus plus 9101 square, square. So we have this. Now let's take the square root of both sides. You have 8374.51. 8374.51 kilopascal G. Now we have gotten this. So now let's get it in gauge pressure. The gauge pressure will now be 8374.51 minus 101. So if you minus, this is 8, you minus 1 here, you have 3. This is 7 will still be minus 1 here is 2. So 0.57 kilopascal. This is gauge. So now we have gotten this. Since we have gotten our outlet pressure, which is actually this is not the actual. Now let's now recalculate our average pressure. The average pressure, which is 2/3 of P1 plus P2 minus P1 times P2 divided by P1 plus P2. So let's calculate the average pressure and recalculate our compressibility factor and use it to calculate. Now to see what should be our final answer. So now we have to times this will give you what we have 9,000 plus 8273.57 minus this will now be 3273.57 times 9,000 divided by 9,000 plus 3273.57. Now let's use our calculator to calculate this. Now we have 9,000. Okay, let me just say 2 divided by 3 times brackets open 9,000 plus 8273.57 minus 8273.57 times 9,000 divided by brackets open 9,000 plus 8273.57 bracket close equal to what? So okay, no, this did not give us the right thing. So now let me calculate this first. So 8273.57 times 9,000 divided by bracket open 9,000 plus 8273.57 bracket close equal to 4,000. So now we now say this minus plus 9,000 plus 8273.57 equal to times 2 divided by 3. We now have 8641. We have what? 8641.87. 8641. 8641.88 kilopascal. So now we need to change the average pressure to PSIG. To change this to PSIG 0.147 PSIG is equivalent to 1 kilopascal. So this is kilopascal. So this will cancel out this. We're just using this to multiply the conversion factor. So our conversion factor times 0.147. So we have What actually happened? Let me see. 8,641.88 times 0.147 is equal to 1,007 1,270.36 1,270.36 PSIG. Now this is the average pressure we're going to use to calculate our compressibility factor. Now let's go there. That means our compressibility factor will now be 1 over 1 plus average pressure times 344,400 times 10 raised to power 1.785 G divided by fluid temperature raised to power 3.825. So the compressibility factor will now be 1 plus, this is 1,270 point what 36 times 344,400 times 10 raised to power 1.785 times G, which is 0.6, divided by 28, divided by 519 raised to power 3.825. Now let's use our calculator to do this. We now have 1 divided by bracket open 1 plus bracket open 1,270.36 times 344,400 times 10 raised to power bracket open 1.785 times 0.6 bracket close divide by 519 raised to power 3.825 bracket close equal to 0.825 0.825. So 0.825 is our Z now. Now let's apply this Z to in this particular problem again. Now we have our P1 squared minus P2 squared all raised to power 0.5 equal to the flow rate times GTFL Z all raised to power 5 divided by 5.747 times 10 raised to power minus 4F times D raised to power 2.5 times pressure will divide by temperature. So that is it. Let me see whether there is other thing that I need to add. No, all is correct now. Now let's use it to calculate. Now we have our flow rate to be 3.5 times 10 raised to power 6 times G, which is 0.6 times the temperature, which is 288 times the length of pipe, which is 48 times Z, which is 0.825 all raised to power 5 divided by 5.747 7 times 10 raised to power minus 4 times 18.11 times 380 raised to power 2.5 times the base pressure 101 divided by the base temperature 288. Now this will be equal to what? Now let's calculate. Let's use our calculator here now. Uh, we now have let me see 3.5 exponential 6 times bracket open 0.6 times 288 times 48 times 0.825 bracket close e raised to 1 0.5 times 101 divided by 288 divided by 5.747 exponential minus 4 divided by 18.11 divided by 380 raised to power 2.5. So we have 3465.75. We have 3465.75. 3465.75. We have 3465.75. So that means P1 square minus P2 square all raised to power 0.5 is equal to 3565.75. Let me see. Okay, this is 4. Then I'm squaring both sides, you have P1 square minus P2 square equals 3465.75 square. Now we have P2 square equal to P1 is 9101 square minus 3465.75 square. Now taking the square root of both sides, you have P square P2 equal to the square root of 9101 square minus 3465.75 square. So let's now use our calculator. So we have the whole of this square minus plus 9101 square equal to the taking the square root is 8415. So we have 8415 point 27 kilopascal. Now 8415. So when you go back, we have 8374.5157. So now we can recalculate our outlet pressure, and we can recalculate our outlet pressure by calculating the average pressure. Use it to calculate our compressibility factor. And now look at the variation. If there is no much variation with this value here, 0.825, we know there will be no much variation with this, because now if you look at this formula all through, you see there is a correlation. There is a correlation. All this is constant. There is a correlation with this value here. So there is a correlation. We now need to go back again and recalculate our Z, the compressibility factor, to see if it's closer to 0.825. Let's recalculate our to see what we get. Now we have this, so now let's say the gauge pressure of this is will now be 8415.27 minus 101. So to get the gauge pressure, so now of the outlets, we now have 8314.27 kilopascal gauge. Let's use this to calculate our average pressure, which is 2/3 times 9,000 plus 8314.27 minus 9,000 times 8314.27 divided by 9,000 plus 8314.27. Now let's use our calculator again. So using our calculator, we say 2 divided by 3 times bracket open 9,000 plus 8314.27 minus 9,000 times 8314.27 divided by bracket open 9,000 plus 8314.27 bracket close. So bracket close, then equal to 8661.66 equal to 8661.66. Is it? Let's see again. 661.66, correct? Kilopascal G. Now to get our Z factor, which is compressibility factor, you have 1 all over 1 plus bracket open average pressure times 344,400 times 10 raised to power 1.785 G divided by temperature, again fluid temperature raised to power 3.825. So we now have 1 all over 1 plus this average. Now to convert this to Pascal, we multiply this by 0.147 psi, which is equivalent to 1 kilopascal. So this will now be equal to what? Now let's just multiply this by 0.147. So we have 1273.26, 1273.26, 1273.26 PSIG. So that is what we're going to use here. So we're now going to use 1273.26 PSIG times 344,400 times 10 raised to power 1.785 G, which is 0.6 divided by 519 raised to power 3.825. Now let's make use of our calculator. So Z will now be Z will now be 1 divided by bracket open 1 plus bracket open 1273.26 times 344,400 times 10 raised to power bracket open 1.785 times 0.6 bracket close divided by 519 raised to power 3.825 bracket close equal to 0.825. So we'll have the same value for Z, which is 0.825. So since there is no difference between this value here and this value here, so the outlet pressure will now remain the same as 8314.27. Will now remain the same as 8314.27 kilopascal G. So this is our final answer, because this value will still give you the same expression. So this is our final answer. Now, thank you for watching till the end. Thank you, Lord. Thank you for watching till the end. Have a nice day. Have a blessed day. Do well to subscribe to my channel and hit the notification bell so that anytime I make new video, you'll be the first to watch. Thank you and God bless.